Today, I thought I will just briefly describe currently where we are in terms of finding very big black holes using stellar dynamics. And then I'd like to go into a bit into demographics, talking about the local black hole mass function and its relation to gravitational waves being probed by pulsar timing arrays. So very briefly, again, these are about local black holes, so not the AGNs or quasars Jenny was talking about yesterday. And here we're talking about using direct dynamical tracers. So roughly in the local universe, about 150 such measurements have been gathered over decades of efforts. And there are four types of luminous tracers that have been used to probe the black hole's mass. The sort of the workhorse is stars because every galaxy center has stars. And ionized gas, masers, and more recently, CO gas, if it's in a good rotating disk, that can be a very good tracer, in particular using ALMA. And our beloved Sagittarius A star, of course, we're blessed with an individual stellar orbit, but when you go beyond our own galaxy, there's no such luck to resolve individual stars. So when we do stellar dynamical measurements, we use integrated stellar light, but still we have a lot of information. So we measure the line of sight velocity distributions of the stars in order to probe the hole's gravitational field. And some systems have independent masses from multiple tracers, famously M87, and famously some of those don't agree. But for some other systems, like the beautiful NGC 4259 that had first Maser's measurement, the stellar dynamical measurement agrees very well. And for the stellar dynamical studies, almost all prior measurements had assumed axis symmetry in the modeling to obtain the mass. But almost all massive elliptical galaxies, they're not flattened oblet rotating disks. And I'm pretty sure they're all triaxial, so the three principal axes are not equal or even axisymmetric. So we have been spending the past several years in making the modeling part ready to do triaxial dynamical modeling. So a couple challenges in terms of observations and modeling part for getting black hole measurements. So spectroscopically, it requires very high signal to noise. It requires spatially resolved integral field spectrograph so we can get information about the stars over a large spatially resolved region of the galaxy. And also, we would like to measure not just the line of sight velocity or the dispersion, but the full velocity distributions because they have a lot of information. So we don't want to assume a Gaussian distribution for the velocity distributions. And we also need spectroscopy for not just within the sphere of influence of the black hole, but out to probably about one effective radius of the galaxy, because a lot of the stellar orbits could be highly eccentric orbits, so they could travel to large distances. So to constrain the model, we want a large spatial dynamic range as well. And additionally, now if we want to study the most massive galaxies and their black holes, curiously, their central stellar light profiles, as I'll show in a second, they're chord, they're flattened. So they're not the sort of cuspy de Vaucouleurs profiles or Sirsic profiles we learned in Astronomy 101. So that makes it observationally very challenging to get enough photons. Modeling-wise, once we get these thousands of constraints over many spatial bins and multiple velocity moments, then we want to make good use of the data. So we don't do virial estimator or even Jeans modeling. We do a full triaxial Schwarzschild stellar orbit modeling. And here are just some highlights of some of the implementations we had done in the past 5 years to get the triaxial Schwarzschild orbit code working and make it fast enough to search for the galaxy parameter space that these parameters we're trying to constrain. So for every galaxy, we obviously have the black hole mass as a parameter, but there is also the stellar mass to light ratio. We do know the stellar light distribution, but we don't know the mass. So that ratio is a free parameter. And then we also need some kind of constraint on the dark matter, not the detailed profile, but the enclosed dark matter, because um, the orbits do go out far enough to be sensitive to the dark matter when it's at a large enough radius. So simultaneously, and now because we have triaxiality, the stellar part of the galaxy is characterized by three axes. So we have at least 6 parameters to probe, and each model is very expensive to compute because we calculate a whole library of orbits. So we also had to implement a new strategy for searching in this parameter space. In the old days, by the nuclear team, for example, they just did it in regular grids, and that went out. That was incredibly, it's not feasible when you're probing 60 and beyond. And they were doing axisymmetric modeling, so it was a lot cheaper. Okay, so I just want to highlight some recent efforts that we're pursuing using Keck's very sensitive IFU called KCWI. So just putting in perspective, M87 at about 6 billion solar masses, the black hole. There currently only a handful of black holes have masses larger than that in the local universe that have been determined dynamically. And here I'm showing the surface brightness profile of M87 you can see on top. So these are all from HST imaging and of the very central few arc seconds of each galaxy. And this is what I was talking about, the non-cuspy profile of these giant elliptical galaxies. And you can see some of these colored ones that we had already been able to get the black hole masses, and they are on the order of 10 billion or to 20 billion solar masses. And you can see they're much further out, but they got giant black holes. And these surface brightness profiles have a additional parameter here, the core radius, which you can determine by fitting a Corsair sig or some kind of local profile to determine this characteristic scale. So they don't continue like lower elliptical mass ellipticals, then the profile will go up. Um, these have very faint cores. And these are some others we're currently targeting with KCWI. And in particular, you see this Abell 85's BCG, the brightest cluster galaxy called Holmberg 15A, at a 200 megaparsecs now. And recently, we're able to determine its dynamical mass of 22 billion solar masses using KCWI. So we have found that the core radius, if you have photometry, it correlates very well with the black hole mass for the ones we were able to measure. So instead of using velocity dispersion of the host galaxy and the famous M sigma relation to pick targets, now we are using large core in the photometry to identify possible host galaxies for the follow-up spectroscopic work to detect the black hole masses. So let me just, and you can see how painful H15 is 4 magnitudes fainter than M87. So we need a very large telescope and long exposure time to get high signal to noise spectra. So let me just highlight the data we're able to get and the modeling we did to obtain this measurement. So this is just a sample of 10 out of 313 spatially bin. We co-add a lot of them to achieve a signal to noise of more than 100. So over multiple years of attempt using Keck's KCWI to get these very nice spectra. And this is in just sample from the central part of the galaxy out to 31 arc seconds in spatial bins. And I just want to show you that the black here, each curve is the data, and the red is the model fit to the spectra, each spectrum, and where we took a library of template stars with very narrow lines, and we ask what velocity distribution do we need to broaden the lines with in order to match the data. So you can see the match is excellent. And from here, we can, from the modeling, from the broadening, we can measure the V, the line of sight velocity, sigma, the second moment, and also many Gauss-Hermite moments, which we use to characterize the deviations from a Gaussian distribution. So we can go out to at least 8 moments when the signal to noise of a spectra is high enough. So then each bin, we have, say, 8 constraints, and we have hundreds of bins. So then we have thousands of kinematic constraints. So to make use of these observational constraints, we perform short orbit modeling using a triaxial code now. So here is just the final corner plot for this galaxy, from which I'm highlighting the black hole mass and the axis ratios for the luminous part of the galaxy, the stars. So you can see the middle to the long axis is about 0.89, and the short axis to the long axis is about 0.645. So it is indeed triaxial. And this is after searching through many models and using sort of a smarter search optimization algorithm to speed up the calculation. And just a few months ago, within the BEX working group, Angelo and others, we all got excited about the shadow size. So the implied shadow size of this whole mass and the distance, if it requires 222 megaparsecs, would be 10 micro arc second. That's pretty nice, except there is a non-detectable submillimeter flux. The ALMA only had Neil did this attempt to use ALMA, but there's only an upper limit. Okay, so one key feature of the local, very massive black holes and their host galaxies is that most of them are very dormant. I think Jenny referred to that yesterday. They may have a little radial flux or here and there, but very quiet. Because in the local universe, big black holes, there's very little gas left in it. Okay, so just put these things sort of in on the sort of well-beloved galaxy scaling relations. So on the left, here I'm only plotting the upper part, the massive part of the whole M sigma relation, starting at 10 to the 8th solar masses for the black hole. And these are just all the sort of among the 150 dynamically detected ones by many, many groups. And versus the sigma, which is the velocity dispersion of the host galaxy measured at a sort of effective radius. So this is the large scale sigma, indicating the gravitational potential of the galaxy. Of course, people have been excited about the positive tight correlation for decades, but I just want to highlight that these several known in red, they're above the M87's black hole mass. They all seem to be above the relation. So it doesn't really work well for massive galaxies. And part of the reason I think is as galaxies merge, ellipticals need to merge to form these giant ellipticals. You can't just have 2 spiral galaxies doing that. You don't get enough stellar masses. I think the sigma doesn't grow much anymore, but black holes can just add their masses. So they tend to pile up in sigma. And we had done some merger simulations a while ago to study these trends. But if you look at black hole versus the core radius that I showed earlier, they correlate very well. Of course, the core radius radii are relatively small scale, and probably the best explanation for this is the cores may be caused by prior binary black hole core scouring, kicking out the stars. So the core really knows about the black hole mass. But observationally, this positive correlation allows us to choose targets with large core radii to get spectra for to measure its black hole mass. Okay. So I just want to now transition a bit now broadly into the demographics. So we're able to continue to measure these black holes, discover them. And one would like to know just how many are there? Is there a local black hole, supermassive black hole mass function that we can trust? And can we use that to then infer and connect to gravitational waves due to binaries? So to do this, we recently examined this question, and the current dynamical measurements, the 150 or so, they were really heterogeneous. So you don't know the selection function. So I'll show you show that histogram, but you really can't use that to construct a mass function that's has the proper selection taken into account. So the standard technique to sort of infer mass function for the black holes is to start out with some distributions for the galaxies. And then we use the black hole galaxy scaling relation, convolve that to transform the galaxy statistics into a black hole statistic. So as I had shown, M sigma doesn't work very well, especially for the massive N, which is our interest here. So with my postdoc Emily Leopold, we thought, let's start out with a galaxy stellar mass function and locally, meaning redshift 0. And there are a lot of people out there who have tried to measure stellar mass function for galaxies over decades. This is one of the basic property of galaxies. And any cosmological simulation will try to try to reproduce local and higher redshift galaxy stellar mass function. So there's a lot of literature behind it. So what's new in our work is we examined, I think the latest, probably the most comprehensive compilation of the local stellar mass function is by Joel Asia in 2020. It was a beautiful set of papers where he compared his results. So this is just a galaxy as a function of stellar mass for the galaxies. And on the right, you can see, so he took 3D HST and cosmos fields. So these are very deep fields, but not very wide, so that he could have the redshift span. You can tell it. He determined from locally about redshift of 0.2 out to redshift 3. And very comprehensively, he constructed how the galaxy mass function evolved. But if you look at their local, this is the lowest redshift bin he had, they have no galaxies above about 10 to the 11.3 at redshift 0, very few. And understandably, because their field of view is small, they are trying to go deep, not wide. And that's what these famous fields were designed for. So as a result, we think they're missing, and all these other works are based on Sloan or some other studies. They're not focused on the local volume. And as it turned out, I have been with Jenny Green and others have been working on the so-called massive survey in the past decade, where we target the local volume out to the Coma cluster, about 100 megaparsecs. It's a volume limited study of the 100 most massive galaxies in the northern hemisphere in order to understand these elliptical galaxies well and to probe their central black holes. So we happen to have that with very well-determined selection. We just select based on stellar masses. So we actually have the data here to complement these very deep studies in redshifts. So what Emily and I did was, but we don't have any volume for the, we don't go faint enough to cover the lower mass galaxies. So we connected the two. We combined Lasia's lower mass stellar mass function. I think those are very well determined. And then we use the massive survey, which we know the survey volume is the selection to our numbers, and then constructed this purple band. And I don't want to go into details, but there are ways of we need to ask, how do we determine the stellar masses? And because these 100 galaxies have been studied with very much detail, so we have both dynamical stellar mass measurements through short-shot modeling for a subset of them, and also for all of those which we could observe from Magellan, we had stellar pop construction, additional spectrum that we can determine a stellar mass. So none of these are based on the so-called SED spectral fitting that Joel or others used. And the reason is we are only studying 100 here, and they were studying thousands. So they couldn't do a detailed study, and we can't. We don't use the photometry they're using. So it's complementary. But for us, we do have these two different types of stellar mass measurements. And the key is they actually agree, as we described in the paper, to within 15%. I think that's actually really good for such difficult measurements. But that brackets sort of our the range we're showing here. But so this is our latest determination of the local measurement. And you can see if you put the massive part here, we predict a higher, more abundant massive galaxies. And I think earlier work was either missing these galaxies or there could be something about the IMF they assumed. Again, this is not an IMF talk, initial mass function. They typically assume Krupa, but all the indications so far indicate that these massive ellipticals, the initial mass function may be bottom heavy. So we can happy to talk about separately. But anyway, so this is our starting point. We constructed a new redshift 0 galaxy stellar mass function. Our goal is to get the black hole mass function. So what we did was rather than using we didn't want to use M sigma, so we used the M black hole and M bulge scaling relation, which had been very well studied as well. And I like this relation because it's a mass to mass relation. So the slope is typically about 1. So it's the intercept that you need to worry about. And there have been a lot of studies of that, black hole on average is about 0.2% of the stellar mass of the galaxy with well-determined scatter. So what we do is we take, it doesn't really matter whose you took, we took, the one I worked on in 2013, but making sure we convolve it with the proper scatter and so on. So we converted our local stellar mass function, this sort of purple band, into the black hole mass function. Along the way, we also compare with some other very famous papers for the galaxy stellar mass function, including Leja. So you can see upon convolution, most of the errors are coming, or uncertainties are coming from the scaling relations scatter. So the black hole mass functions, we all agree much better than the stellar mass function. And the reason is it's dominated by, the spread is dominated by the scaling relation, not the galaxy mass function. Okay, I'm showing a few other sigma-based black hole mass function using M sigma relation just for comparison here. Okay. So from this black hole mass function, then I'm just zooming into this, then we can ask, within this massive survey volume, which we know very well, it's out to some distance in the northern hemisphere above deck of -6, how many black holes are known? And that's shown in this histogram. Okay, so you can see, of course, this is just all the dynamically measured known ones. So it's very comfortable at the high mass end. Basically, it's consistent with the current known population. And you may think there's a deficit here between the dynamically discovered and the predicted ones based on stellar mass function. But this is just because no one's going out and measuring these black holes. There are a lot more out there. It's way too expensive to target every single one. Okay, but I just want to highlight the high mass end. We don't need like 10 of these 30 billion solar mass black holes. For example, Sato Polito said they would need to account for the low frequency gravitational waves. Okay, so let me now turn into the low frequency gravitational waves. And it was motivated by this paper. And so with the black hole mass function, we can do very sort of simplistic calculation, assuming each current day black hole experience one merger with some redshift distribution, some mass ratio, and then you can infer, on circular orbits and a lot of simplifying assumptions. And then you can kind of integrate these functions using Finney's prescription in 2001 and just kind of get an estimate for the inferred gravitational wave strain level. Okay, so on the left is the kernel of the hc squared, but on the right is the amplitude of hc, and this is determined at a frequency of 1 over 1 year. Okay, so some of you may have seen the pulsar timing arrays, different 3 collaborations had reported these levels, and the inferred low frequency gravitational waves based on our black hole mass function is very comfortable with this. So I think it's quite remarkable that just by doing these simple integrations of that black hole mass function I show, it's in the right order of magnitude. And the prior paper was very concerned that when they used sigma, so they didn't use stellar mass function, they used a galaxy velocity dispersion function. They found some number that was, about a factor of two lower. But given all the assumptions that went into these calculations, I think overall, my sense is it's incredibly consistent, and it is remarkable that sort of just the, simple calculation for the black hole mergers come out to be the right order of magnitude. Okay, so some caveats is these calculations that we're doing here is literally this integral. Okay, and you can see this has a characteristic f to the minus 2/3 for HC dependence, but that assumes the orbits are completely driven by the gravitational waves evolution is in that final phase. And here we just did, as I said, simple Q is the mass ratio of the merger, and the redshift Z is the redshift of the prior merger. So only single generation. So if you account for it properly, it probably could be higher, the amplitude. I just want to contrast this with there's a lot of work right now, especially within the nanograph or pulsar timing array teams. We or they, together, we do a much more detailed Monte Carlo kind of population synthesis calculation, and I call this kitchen sink. And there are many, many parameters, and this is in the initial paper that came out, is showing the strain versus the gravitational frequencies. And there could be environmental effects that flattens the slope and so on. So there could be a lot of modifications to the simple calculation. Okay, and either method has its pros and cons. So I just want to highlight that. Okay, and then just one final implication of our black hole mass function is you can just integrate and ask what's the black hole mass density in solar masses per megaparsec cubed. And that's shown here compared to the quasar luminosity inferred a number. And they are somewhat higher. Again, error bars are big, but I think obscuration, lower efficiency for the Eddington efficiency could easily raise the quasar numbers. So I'm not too concerned about this kind of if anything, the local number should be higher. Okay, so to summarize, I want to say that so this attempt to study the local census, I think our higher amplitude stellar mass function solves some puzzles. There was a reported lack of evolution in the Joel Asia's work that the stellar mass function appeared to be the same between redshift 1 and 0, and that's very puzzling because we know galaxies merge during these 10 billion years. So now that our mass function is higher at the high mass n, it allows for some evolution, which we would like to have. And as I mentioned two just now, and then three, that actually the stellar masses, we're very pleased to find that our two methods agree quite well. Okay, and now I just want to mention for Bex, of course, we continue to talk about the targets and so on, but I want to just also say, I think the supermassive black hole binaries within the pulsar timing array community, now the focus is on the continuous wave detection. Can we detect individual sources? It will take some time, higher signal to noise. And how do you get the electromagnetic counterparts? But unlike LIGO, where you don't know where the events are, which galaxy and where in the galaxy the events would be, for us, at least we know where the big galaxies are because there are lots of galaxy surveys. And we know the big black holes will live in big galaxies. So we are doing some demographic sort of mock maps. We're trying to construct that, at least knowing where the hot spots are. The only thing we don't know is where the binaries are. So if PTA one day can sort of pinpoint some part of the sky saying, we think there is a binary there, I think it's great for us, Beck's team, to discuss how we would sort of communicate with the PTA team. I'm part of the nanograph team, so I would love to continue thinking about this. Thank you very much.